In this recording, we're going to look at compound interest, which is a pretty useful topic, especially for anyone who has any interest in money. Most of us do. So, compound interest basically has to do with the fact that when you put money in the bank, that money makes interest, and then you're earning interest not only on the initial amount, which is called the principal, but the amount that you earn in interest. So it's the compounding effect. So let's start with a simple example here. We have a $500 initial investment with a nominal interest rate of 4%. Now on the back side of your sheet, nominal interest rate is defined, but basically what it means is it's what the rate is in name, okay, like nombre in Spanish. It's its name, but really its effective rate is different. Often it's a little higher because if you start compounding more often than once a year, you're going to get a little more than 4%. Okay, so let's work this example out. So we want one time per year, and we've got 10 years. We've got $500. Okay, so why don't you set up a calculation here and play the recording. So hopefully you did 500, our principal or initial amount, 1.04, there's our growth rate, to the 10th power. Okay, that's our calculation, and we can work that out. It's going to be 740.12 cents. Well, what if it were 4 times per year? Why would it not make sense to multiply by 1.04? Think on that for a second, then play the recording. Okay, hopefully you realize that you would get much more than 4% over the course of the year, right? All right, so that doesn't make sense to give you 4% every quarter when you're supposed to get 4% for the whole year. So instead, what would you assume you would get per quarter if you get 4% over the whole year? Hopefully you jotted down something. Hopefully it makes sense you'd get 1%. So if you take your yearly rate and divide by 4 quarters, that would get you your quarterly rate. Okay? So let's figure out then if we did 10 years compounding every quarter. So that would be basically 40 quarters, right? 40 compoundings. Okay? So let's consider that calculation. You're going to start with your 500 again. But instead of having 1.04, we've got 1.01. So we're only getting 1% now, but we're getting it more often. We're getting 40 compoundings. When you do that calculation, let's see how it comes out. It works out to be $744.43. A tiny bit more than if we just left our money in there and they calculated it once a year. That's the value of compounding. Okay, so the pattern is straightforward as it says here. Shorter compounding period, like once a month, once a quarter, once a day. We apply the interest more often, but at a lower rate, a fraction of that. Okay? So go ahead and work out exercise 2 and play the recording when you're ready. Okay, so something like this. We've got $1,000. Got a 2% rate, so we'll go 1 plus, but instead of doing 0.02, I've got 0.02 divided by 12, because there's 12 months in a year. And then the exponent, well, it's going to be 12 times 20, because for each of those 20 years, we're going to do 12 compounding periods. And then when you do the math there, you get 1491.33. Choice 2. So, if we want to generalize and write a formula, here's a pretty useful formula. Okay, we've got A of t. Well, we've got our initial amount, and then we've got 1 plus, and you saw what we did here. We divided the rate by the number of compoundings per year. So if it's just once a year, we're dividing by 1. That doesn't change anything, right? But we're going to take that rate and divide by n compoundings per year. But then we're going to compound it more often, right? So it's not only t power, it's n times t. That's what we did here. We took the number of months per year times the number of years. Okay. So, as we kind of already explained here, the effective rate is what you really get when you're compounding it more often. So let's check this out. Let's just say you had a 5% rate, which is absurd. As I've said in other videos, you'll never get 5% in a savings account. Maybe in like an investment or something, a money market account or stock or something. That would be something you could see. Okay. So what's the effective yearly rate to 2 decimal places if we compound quarterly, monthly, or daily? So why don't you get as far as you can and then play the recording when you're ready. Okay, so for the quarterly, we don't even know the amount, the initial amount. We'll just leave that blank. But the rate would be 5%, get my leading 0 in there, divided by 4, but then you're going to get it 4 times a year. So when you do that math, 1.0509, make that into a percent, rounded off to 2 decimal places. So in fact, the effective rate, what you're actually getting, is 5.09%, not just 5%. Go ahead and do that for monthly and daily. Okay, so if you haven't done so, please take the time to do this and then play the recording. So as we see, the more often you compound per year, the better the effective rate is. And there's not a huge difference between monthly and daily, but it is a little bit. Finally, we could continue. Maybe we do it every hour, every minute, every second. Eventually, this n would approach infinity if we do it continuously. And in that case, this approaches a limit which gives rise, as it says here, to the use of the natural base, the number e. So let's look at this number on your calculator. This number exists over here in 2 places on your calculator. One is right here, e to the x, and the other is right here, e. So if I just do second divide, shows that number, 2.7182818. It looks kind of like it repeats here, which is a little misleading. It looks like it goes 18281828. It does not repeat or terminate. It's a irrational constant, kind of like pi is. So another place you can find it here is e to the x, because so often we use e as a base with an exponent. They built it in so you can go like second e squared and hit enter. All right. So let's check this out. This is the continuous compounding interest formula. So if something is growing at a continuous rate, like a natural process, like a population of bacteria on your hands right now or something like that, it's not stopping to grow at intervals like quarters or days or months. Instead, it's growing continuously, and we use this formula. So let's consider this example. We've got a $350 initial investment, and we're going to have a 2% continuously compounded interest rate. It's really important to underline or highlight the facts that are given to you, right? And not only the rate, but how often it's being compounded per year. So let's look at what it would be after t years. Okay, so applying this formula, the continuous compound interest, it would be something like this. A of t equals our initial amount, that's our p, principal, times e to the 0.02 t power, where 0.02 is our rate, t is the amount of years. So would it be in 20 years? Well, go ahead and evaluate that for the recording when you're ready. So hopefully you took time to work this out using your calculator or the Desmos calculator. Alright, when you do this math, it works out to be $522. If you're wondering, what do we round to? You should always round to the nearest cent, because we can't go more precise than that, unless it tells you to round to something less precise than that. We can't really work out this question algebraically. Later we will be able to. For right now, we will skip this question. We could solve it using a table or graph, but later on we're going to be able to solve it using something called logs. Finally, what is the effective annual rate? In other words, if this were done once a year, what is the effective rate for this investment? And so essentially we're just going to take this portion of it, this e to the 0.02 power. Remember, e is a mathematical constant. It's 2.72-ish, right? We just looked at that on the calculator. 2.72-ish. And if we raise e to this power, 0.02, we get 1.0202, which we can interpret here to the nearest hundredth of a percent. That's about 2.02% effective rate, a little better than the 2% nominal rate. That's the effective rate per year. Thanks for watching.